Yeah, thank you very much for the introduction, and thank you very much for sticking around for this last session. And yeah, I hope you're going to enjoy it. I'm going to talk about Apache Flink and Apache Kafka, a bunch of, kind of contrasting a bit the philosophies, let's say, between Flink K-streams. Also, a lot of the use cases that we've seen over the last weeks even, where we see Flink and Kafka kind of pulling the wagon together pretty well, and yeah, I want to share those. I'm going to start just very briefly introducing myself. I'm a co-founder of Data Artisans. We're the original creators of Apache Flink. That was around about 3.5 years ago. And we're also offering the Data Artisans platform, which is an enterprise stream processing platform built on top of Apache Flink. I'm going to do a very brief introduction to Flink. I hope most of you have actually heard of it before, or at least roughly know where to place it. Like from a very high level pitch, Apache Flink is a system for stateful computation over data streams. It's not a system to store data streams, unlike Kafka is the log that stores events. It's a system to compute over streams of events. And it has a very broad interpretation of that setting, right? It has, there's the classic stream processing, real-time results from data streams. Flink's interpretation of stream processing also generalizes well to batch processing and to event-driven applications. So it really sits as the processes that orchestrate computation over data streams. It consumes from streaming data sources like Kafka or other pub subsystems. But also, other storage systems, databases, file systems, and it produces into various forms of syncs. It has a very flexible sync interface, but the most common use cases that we see is actually producing, again, into things like Kafka, producing into file systems, Parquet files for later analysis with SQL systems into databases, or directly calling RPC into applications. The idea of Flink is really computation over data streams, and I know I'm repeating this, but it's like a very core concept in Flink, and the interpretation of what a stream is a very broad interpretation here. So everything is treated as a stream internally, as a potentially unbounded stream if you're running a continuous stream processing application, or also as a bounded stream if you're actually looking at a finite piece of data from the past. So from Flink's perspective, if you're actually running a computational job over, let's say, a bunch of files that sit in HDFS or S3 or so on, from Flink's interpretation, that is a stream processing job over a bounded data stream. So all these files together just form a stream from its perspective. And bounded streams can start in the past and extend into the future. Unbounded streams can start very far in the past and extend infinitely into the future. So this combination of also taking data very far from the past and also real-time data kind of together is, it's very essential here. Flink has a bunch of layered APIs which you use to define the streaming computations. The API that most folks actually start with is the data stream API, centered around streams and windows. I'm going to have an example in slightly larger print than that later. It has an API that's a bit more low level, which gives you very raw access to the core components of Flink, which is events, streaming events, state, a very flexible notion of state in various shapes with persistence, exactly once guarantees, and time. I'm not going to dive much into time in this talk. Let me just say at this point in time, the idea of time in Flink is actually, it runs internally different clocks. For example, a processing time clock that tells you what time is it now, and an event time clock driven by a mechanism called watermarks that tells you what time is it in my data stream. Those can be vastly different from each other. For example, if you're reprocessing data from the past, you're just starting a new application and you're still crunching yourself through the data from last month, then the event time clock will be within last month. So you can use those to build applications that take both of these into account. And then there's a high-level API on top, which is actually not too unlike KSQL. There's differences in the nuances. It's built on the idea of dynamic tables, so there's we also like this idea of stream table duality. Yeah, I have an example for that later. So roughly the data stream API, yeah, it's a Fluent API. It describes basically streaming data flows. It looks like you expect one of these APIs to look these days. The lower level API, the process function API, which gives you rather raw access to state, allows you to take individual events, put them into state, retrieve them from state, schedule timers into the future. These timers are actually also like persistent callbacks aligned either in processing time or in event time, so you can actually make these deterministic applications that process well even if you're computing through data in the past. And on the high level SQL, as you know, SQL. I think a slight difference to its KSQL, just to relate to the previous talk, is that we try to stick with ANSI SQL. And one big reason why we try to do this is that we're trying to bridge a gap between batch and stream processing also with this SQL API. So remember from the past, from Flink's perspective, you can also treat the past as a finite data stream. So the idea of this SQL statement is if you bind it to a time range that lies in the past and you execute it in batch, the resulting table should be exactly the same as if you actually go through the stream that produced this table from the past, execute it, and keep incrementally producing the result and outputting more and more and more. In the end, they should both exactly arrive at the same result. This is one way to try and bridge the world between batch and streaming in a SQL way. Details on that is actually a talk in itself. I'm happy to also answer questions afterwards, but today, I'd actually like to focus more on, the core of Flink itself and a bit of how it, interacts with Kafka. Just to give you an idea of what is Flink actually used for. For those of you who have followed the Flink news a bit, you might actually know some of these use cases. It's actually being used for some pretty impressively large use cases that still astonish me when I look at them. So. Arguably, the biggest user of Flink that we know of is Alibaba. They have a slight modification of Flink called Blink, which has a few internal patches, but it's fairly close to the vanilla Flink by now. So they've been contributing back those patches over the time. And this actually runs their stream processing recommendations during the Singles Day, which is this crazy global shopping festival in China. And the details are maybe lost here in some of the comments, but they're running stateful stream processing jobs in Flink, which actually have tens of terabytes of state inside the stream processor. That's not working against an external database. It's just like the internal state that where you actually remember state from events and that you use to interpret the next event to contextualize it. Other use cases, this use case is not large in the sense as it's as stateful as in it doesn't keep the tens of terabytes around, but it keeps a pretty decent event rate. And we already have a nice example of Flink and Kafka working together here. So Flink is used here. That's it's a use case from the data routing pipeline of Netflix. It's used here in combination with Kafka to take the raw ingest stream, pre-process it, route it downstream to various systems. S3 for archival, Elasticsearch for search, and further Kafka topics for real-time consumers. So that's basically Flink in the large. I just want to mention that you don't have to have 1,000 nodes to run Flink. You can actually run it in a single process as well. And there's some users that put them also on an IoT gateway. If it's just like a single node, of course, there's a compromise in fault tolerance. If that node goes down, it's down. But at least you can compute on the node. You don't need like a terabyte cluster in order to just get started with some stream processing. And it actually works pretty nicely inside the IDEs for debugging as well. So in this talk, I've kind of tailored this talk a little bit towards a Kafka audience. I kind of hope that most of you are roughly familiar with how Kafka Streams works, at least with how I assume Kafka Streams works, to be honest. So I would like to use this session to kind of contrast a little bit the difference in the design decisions that we made at the beginning, which kind of acts as a good foundation to understand how Flink and Kafka kind of complement each other very well. And I'd actually like to start with this metaphor, which I think fits the day very well because we heard the keynote this morning. This metaphor, event sourcing and the memory image, is actually taken from a blog from Martin Fowler. So there we go. You can think of that the basic idea, when we started to do Flink and we thought of, okay, how could you do fault tolerance in a streaming system? We were then assuming it's a system that's independent of other logs, other message queues and so on. How do you do fault tolerance here? And one model that we really liked is this idea of just assuming we can replay some of the events, because that seems to be quite common. Many message queues. Kafka supports this in a stellar way, but it's kind of an assumption that you can make to work also with other systems. If you actually have that, then you take your event log, source the events, and then you have your process, and you just work in the process with your events. You do whatever actually in that process. You don't really need to worry about too much what you do. And then there's something that periodically in the background just takes a snapshot of the memory of that process and puts it to the side. It should roughly better exactly remember actually where exactly in this input event log it was when it took that snapshot. But once you've actually done that, when you have a failure, what you do is you can bring that memory image back, replay the remaining events that you had since the last time you took that image. You've kind of built a fault-tolerant system, right? That's more of a theoretical model than a practical one, but that kind of is the inspiration for how Flink works in the end. So that kind of captures one process. Now a streaming program in the end, no matter how you define it, if you define it in a Fluent API, if you define it through something as SQL, it usually ends up being a flow of operators, right? You have some sources that connect to some source systems that route the events through some other operators, shuffle them around. They interact with some storage. They're going to produce some result. So what you do need to do is either, if each one of those operators here wants to be able to take this memory image, how do we do that? We could try to make each stage individually replayable, or we could try and say we do the snapshots in a consistent distributed manner. So let's assume we just have our events flowing here, and then once in a while we just sweep over the topology and basically take a snapshot that's aligned across all operators such that a replay from the very beginning allows us to reconstruct transitively all memory images. So, and then, if something goes wrong, we can just, restore these memory images and start replaying. And at the very beginning, you actually need to really replay events from the source. So that just means you have to remember the Kafka offsets where you were when you took that snapshot. Now, why were we so keen on using this as an architecture? So one thing to really observe here is that there's no boundary in the flow of events here at all. There's no mini batch. There's no writing to some persistent storage immediately. No replication of intermediate data or anything, right? Which is kind of a nice property, right? It allows you to get this thing with really low latency if your network stack is built in the right way, and it allows you to do this whole thing with really high throughput. And if you remember, we're looking back at this broad interpretation of use cases, batch processing, right? For batch processing, you actually need to be able to get a system that can shuffle, operator to operator, just shuffle through memory and network as fast as possible. You don't want to write to disk intermediately. Otherwise, you're in the MapReduce game, and then the next one that is the Spark game, the in-memory to in-memory kind of beats you. So that's why we wanted to say, if we actually want to be able to do batch processing at all, we need to have that in our architecture. We need to be able to do memory to memory work. So on a failure, you restore these snapshots. I've already outlined that there's no barrier boundaries. Low latency is really good. High throughput for streams that go from operators to operators. A very nice property of that is actually makes shuffles very cheap. I mean, they still cost network bandwidth, but if your network is good, like shuffles are not. You have to worry way less about shuffles than you may be used to. It handles large state fairly well, because if we actually look at the snapshots, what they take, they take the size of the state. So the snapshot is always order of the state. It's not order of the number of events. And state is typically strictly smaller than number of events. I already said it's something that supports fast batch processing, and it also gives you the ability to support a lot of different types of states and timers, because you can use fairly flexible data structures as long as you are able to capture them into a snapshot. Now, you may initially think, okay, God, this sounds cool and flexible, but isn't that terribly expensive to do? And in the naive way, it definitely is terribly expensive to do. So I think for around about maybe a year, maybe a bit more, Flink has this notion of supporting incremental snapshots. So if you actually increase the size of the state inside your streaming application, the snapshot size per snapshot step can actually still retain rather small. It's not always strictly the same. It depends on how much changed, how much was compacted away, and so on. But it's kind of a constant small size rather than increasing all the time. And if you remember my previous slide, the notion of when you have failure, you kind of restore all the entire streaming topology to the previous snapshot. That's kind of a conceptual model. You don't have to physically do it like that, right? Oftentimes, if only one node crashes and all the others still retain their data, you can kind of do a soft rewind. Think of it like a bit of an you undo the changes that you made since the last snapshot, and then just like redo them from there. That's actually mainly done to compensate for cases where there's non-determinism in the program or in the network, which is actually a fair assumption to make. And there's a lot of there's internally the whole state support of Flink is based very heavily on multi-version data structures. So we're heavy users of RocksDB, and we don't only use RocksDB in a key value way. We really make use of its checkpoint and snapshot feature, and the way that it internally keeps multiple versions, sees if there's somebody to still hold on to a version, when can a version be compacted away, and so on. And the same thing is also true for other implementations of the state. So there's, when you don't use RocksDB, you typically use something like an internal hash table, which is a multi-version implementation of a hash table that is able to do asynchronous background snapshots and hold on to these versions until we can release them. So this is a very interesting model to build a system that can actually, that can sustain a low latency and high throughput stack quite independently, without having to make the assumption that you have something like brokers at your disposal also to work with. But there's actually a few other things that you can do with this model pretty nicely. So assume you have a program. It looked like that, and at some point you say, okay, gosh. In order to take the application to the next level, we need to modify this program. So we'd have to do an upgrade, but because we have a stateful streaming program, we don't just kill the containers and start new containers with the new code. We also kind of have to worry about getting the state into the new containers. And maybe the application changed a little bit. Maybe the state is no longer in the third operator, so it now goes into the fourth, or I don't know. So there's a way in Flink, the snapshots and the applications are kind of loosely matched by IDs, and there's certain degrees of flexibility you have when you restore a program to actually describe how the new program should resume the old snapshot. So you can start to, within reason, modify the program and actually restore the snapshot to that program, which is a very interesting feature when it comes to, like evolving programs over time, evolving them in a stateful fashion, not losing state. This is especially helpful actually in cases where you may not be able to just like rebuild the state in your program by reprocessing because your input doesn't have infinite retention, or because your input some events of your input that matter in the state have exceeded the retention period. So that's actually especially for use cases that have a very high load on on Kafka topics. It's quite an interesting case because you will have a limited amount of retention, and you don't have to worry about not being able to rebuild the state if you can, like carry the state from one application to the next with the help of a snapshot. So a common way that we see the snapshots being used is folks just, while they run the streaming application over the stream, just paradigmatically take those snapshots kind of as an archival. What did the application look like at that particular point in time? And these archives can be actually fairly interesting. So for the sake of this example to make sense, I'm actually assuming that we're still within the retention period of the stream here in Kafka. If you then figure out, let's say a day or two later, that there's something that was happening here that there's an incident of interest. I don't know. There's maybe a bug that you want to debug, or I don't know. You made a decision that you think you shouldn't have made, and you want to figure out why actually did you make that particular decision. You can take the latest prior snapshot, create a modified version of your jobs, say something that filters out exactly a specific user ID, and runs it through a separate path to maybe output more trace output, or more debug logging, more than you can, like in your live production, afford to make, because otherwise you just overwhelm your logging system with all the detailed information about every event. So you can take this particular job, resume it from that snapshot, and say run it over a bunch of events from the past. Again, this example assumes that at least for that amount of time you still have the events retained in Kafka. Another thing that could be interesting is, let's assume that your event stream actually looks more like this. It's not strictly a continuous stream of events. It's nice to think about it as a continuous stream of events, but it just happens that you work for an industry where things happen end of day, largely. And you can run a stream processing application, but there's a fair chance it's going to idle 20 hours of the day, and then it's going to go really hot for 4 hours of the day. So you could go and say, I'm running this application, and at a certain point in time, when I'm end of my hot period, I'm taking a snapshot to shut this thing down. And then I'm restoring this from the snapshot, running it again, shutting it down with the snapshot. And you do this again and again and again, and what you kind of have is almost like a batch job, with the nice exception that you've actually modeled it as a streaming job. So you don't really have to worry about how do you care, let's say, in-flight stuff, like let's say whatever transactions or trades that haven't settled exactly on that date that kind of need to be carried into the next side. You don't have to really worry about what happens with the boundaries of the batch jobs, right? It's still conceptually a streaming job continuously. There's no interruption of state. There's no boundary to worry about, because everything that's not been fully resolved between here and here is exactly what is part of the snapshot, what you restore into the new applications, all the pending sessions. So, so much for why is it interesting to actually build a stream processor based on such a model like flowing events and snapshots. I want to spend a few words on saying how we actually integrated Flink and Kafka. There's a few interesting challenges in there that at the very end I can actually, if I have a bit of time left, I'd like to dive into some of the technical details. Let's see if we get to that. On the reader side, actually, we've been working with Kafka since version 08. Very early on, had a reader that provided exactly once semantics. The checkpoints in Flink actually checkpoint the Kafka offsets. So whenever Flink internally commits a checkpoint, that's for for Flink itself, that's the point where it says, okay, these are the offsets that we resume from. It commits them back to Kafka if you want to, but because to really have atomicity, you need to have like one atomic kind of commit operation that at the same time just the offsets and the state. So we kind of had to move that into Flink. Over the last versions, it had, like the Kafka reader has gained abilities for dynamic topic and partition discovery. So you can give it a certain string where it periodically pings the brokers and picks up new partitions and new topics that match that expression. We've actually Flink is fairly frequently used also to consume multiple topics within the same reader. So that's one of the ways that, for example, Netflix uses Flink with Kafka. They spread their load over multiple Kafka clusters for various reasons, just to keep the load or the number of partitions of one Kafka cluster sort of under control, and then they kind of use Flink to bridge between the different Kafka clusters. Another thing that we've integrated in the past is actually to make the Kafka consumer, to make the Flink Kafka consumer aware of the individual partitions and tracking watermarks individually per partition, which is pretty important to get correct event time results if you have skewed distribution across partitions. On the writer side, we've also been working with a few versions, and I would say the most interesting addition has been the exactly once producer ever since Kafka 0.11. I have details in the later sections. Actually, kind of a fascinating integration, I think, between checkpoints acting as something like a non-blocking two-phase commit coordinator for transactions that Flink orchestrates in Kafka. So it uses the Kafka transactions, But because it has a slightly different model there, we needed to do a bit to bridge this world. So you can think of it roughly like, if you know how two-phase or three-phase commit works with distributed databases. It's a little bit like that, just that the individual operations are non-blocking, they're not blocked on voting delays. Flink will just roll over the Kafka transaction, start new transaction, and as soon as the checkpoints start to acknowledge it will commit them. And it will take care that if there's failures in between, it will resolve them properly, either in an abort or in a commit, depending on whether this is a correct checkpoint or it was an aborted checkpoint. So some interesting use cases. How is Kafka and Flink used together in what we see? So it's actually used together a lot. I would actually venture to say that for Flink applications, probably Kafka is the most popular source together with file systems like HDFS and S3. So HDFS is S3 for static data, Kafka definitely for dynamic data, and by far. So very often we see users building applications like that. Kafka topics, Flink applications between the topics, producing downstream into more Kafka topics, being again consumed by a Flink application, producing into more Kafka topics. So kind of chaining these streaming applications together. Let's make a few very concrete examples, and these are actually taken mostly from presentations and other conferences where users spoke about Flink and Kafka. So we already had this one here, data streaming, data stream parsing, and routing. So Flink basically taking the raw data from Kafka and distributing it across different systems. With I think the feature that they really liked here is the ability to directly produce into various different systems with good consistency guarantees from Flink directly. These streams are extremely high load, so every intermediate topic that you put them to is actually costly at this point here. So this was a feature that they liked a lot. What we're seeing, especially in the recent weeks and months coming up a lot, is actually more machine learning pipelines. This is maybe I should actually switch the slides. Let's actually start with that. That's the simpler example. That's an example from Uber looking at like machine learning based real-time optimization that takes a lot of different things into account. This is used for various different things. I think the example they were mentioning this talk was estimated time of arrival models here, which is a pretty essential thing for the planning of rides. So it's a fairly classic online-offline solution for machine learning. You have the initial raw events coming in through Kafka. You have some form of ETL process getting them into a data warehouse. You have an offline job that does model training and that has a set of model features that it produces. And then you have a real-time job which does the feature preparation and then actually takes this model to make the real-time decision and decide what to do with that particular event. This case here is a little more complicated because it's not just such a strict division between offline and online learning. It has a lot of functionality also on the online path where certain features are gathered on the fly, are updated on the fly, and there's like happy paths and fallback paths depending on how does the features and the models currently look like. So various different routing strategies depending on where data comes from. But we're also seeing again here there's a feature store for for some offline trained models. There's the online fire hose of events coming in, and then there's just a slightly more complicated logic in the sense of where does the resolution go depending on the quality, the freshness of the model. One thing that we have actually started to see a lot, and I would personally say that's because the streaming system is getting actually more mature, is real-time and historic, combining real-time and historic data. So I think when we're talking with users maybe a year ago or so at conferences and so on, a lot of them were like very much talking about what do I need to do to get stream processing in production and so on. And this is actually something that's sort of come up over the last months, which is something that you worry about once you actually have stream processing in production. It's how do you actually take your real-time events, often in a messaging system like Kafka, together with all the old data, the distant past. And very often these actually live in different systems. So there's the real-time data in Kafka that be hours, days, months, depending on your data rate, the capacity of your brokers. But almost always, eventually, there's some bulk stored involved. So data ages out of Kafka. Maybe not every event per se, but a bunch of events is often then ingested, let's say in a compressed format like per K or a C or so, into a bulk storage. If you want to do this nice thing of you just interpret everything as a stream. Let me start with a new application. Let's say it's a recommendation model, and I don't want to do this whole offline online kind of thing. I want to buy into this everything streams philosophy. So just say, yeah, I'm writing this application. I'm just starting it at the beginning of time. And it's going to crunch through all the historic data first. And while it does that, it's kind of building its recommender based on these events. And at some point in time, it's gone through the past, and it's kind of caught up with the present, and it's going to work on the live data. So it's actually going to output predictions and keep updating the model with the live data. So this kind of means that you have to sort of form a stream that starts with the data, in this case in S3, and then switches over to data in Kafka. Or kind of, it's a bit of a concatenation. It's, if the data is small enough, you may say, yeah, what the heck, let me just re-ingest it. But from a certain data size on, you might not want to do that anymore. It might not really be a feasible or efficient thing to do. So this is actually taken from a talk from Lyft 2 weeks ago at the Flink Forward conference, where they were explaining how they actually use Flink to do this. They call it bootstrapping of state. So state being the stored context in the stream processor, be that the recommender model, the user sessions, the counters, metrics, the state. And in this slide it says kinesis, but images as well read Kafka there. Like these things. For the sake of this example, they were pretty much interchangeable. We've heard actually about CQRS applications earlier today, and there's a very nice example. It's actually a company from London. That's why maybe even someone from them is here today. It's the way of building a social network over data streams with Kafka as the event log, the source of truth, and Flink being the state of the world materializer. And they've really illustrated very nice in a series of blog posts how they do that. With some shared log where you have a blue and a green variant that independently compute states of the world, and you can mess with one side, see if you can tweak things, and if it's good, then you throw the load balancer that way, and if it goes bad, you throw it the other way. So it's very close to what we heard this morning in the keynote. Like how does event streaming actually help you with A/B testing and so on. It's kind of that in essence. Where we also see the combination of Flink and Kafka being popular is when you need kind of sophisticated time semantics. So sophisticated time semantics, what do I mean with that? Apache Flink implements very much the data flow model that you may know if you followed some of the blogs from the Google Dataflow folks or from Apache Beam, which gives you a configurable trade-off, the watermark between event time and processing time. I like to phrase it usually the other way around. I'd like to say the watermark is a configurable trade-off between data completeness and latency. The further you always in real-time processing can atone between those two sides. You may want to hold it back just a little bit longer because you might get a more complete view of your data, some more events that are actually relevant to this particular decision. But then you might not want to hold it back too much because otherwise, you're going to violate your SLA. But you also may not want to emit each intermediate state because it might just be meaningless at the beginning. There's a certain point when you say, okay, from now on it starts making sense, but how much longer do I really want to wait to get a good trade-off between throughput and latency? And that kind of configurable trade-off between throughput and latency, that is the mysterious watermark in stream processing. So when you actually do so Flink is actually a way to work with these watermarks, and you can use them in very flexible ways. You can actually do very low latency watermarking implementations that run in actually run in the tens of milliseconds in this specific example. This is from a presentation from ING about the feature. I think that part is the feature assembly for the fraud detector that they run. And yeah, so one other part where we see people really like Flink is the idea when you start to want to keep really large state in the stream processor. I have a few more minutes left, so let me quickly talk about an outlook, like what are we working on at the moment, and then maybe dive a bit in the snapshot and transaction integration. One project that I personally really like and can get excited about is this collaboration between Flink and Beam in opening up the ecosystem to a few more programming languages, right? So stream processing, if you're a Java and Scala developer, chances are you're in good company. If you're a developer in Python, maybe in Go, it's kind of tricky, right? So the idea of this project is to build a language portability framework within Beam and use this to plug in languages like Python and Go. And it has kind of a very, very interesting architecture based on co-located containers and so on, which allows these languages to run without the compromise of that we otherwise very often make. All the heavy lifting is still done in the JVM, and it's only a very lightweight SDK that runs for this specific language, which makes it both easy to add more languages, and it means that you don't have to really worry about maintaining large state in Python or in Go, or making sure you get the time semantics exactly right, like in the Java implementation. We're about to release Flink 1.5. It's been a few weeks of release process and a few release candidates. It's a pretty big change that we made to Flink. A big change to the process model, where we want to better support both frameworky style and library style to integrate with stream processing, because, and I have to actually go back to the beginning again, with this broader interpretation of streaming that we have, more like event-driven applications and batch processing, there's really no clear way to say this is how we want users to interact with that. We want them to think of it as a library, or we want them to think of it as a framework. They're really good cases for both worlds. Really depends on exactly what your philosophy is and what you want to do. And we've gotten this as a feedback whenever we said we actually want to switch it to that one. No, for that one. So we kind of reword the model to come to a way to actually support all of those modes. There's a lot of stuff going on. You can actually see there's quite a bit of stuff that we're still doing within Flink. We're still doing improvements to the network stack to say, under certain forms of back pressure, we can guarantee better throughput and latency and better checkpoints. We can get faster recovery of large state and so on. So this whole work on the snapshot model is very much still being improved. But at the same time, we're also working quite a bit on more API features like managed broadcast state, interactive SQL client, and so on. So it's still an ongoing journey. That's it. Thank you very much.